This topic which we'll be studying today is molecular orbital theory. So topic we'll be studying today is molecular orbital theory, that is MOT. It was given by Hund and Mulliken in the year 1932. According to this theory, in the molecules, the atomic orbitals lose their identity and the electrons present in them enter in new orbitals called molecular orbitals. The molecular orbital is not associated with any particular atom, but it belongs to the whole molecule. So according to this theory, whenever the atomic orbitals combine together, they lead to the formation of some new orbitals called molecular orbitals, and such orbitals are the orbitals of the whole molecule, not of a particular atom. Now we shall have a look at the salient features of molecular orbital theory. According to this theory, in the molecules, electrons are present in new orbitals called molecular orbital. Next is, the molecular orbitals are formed by the combination of atomic orbitals, and the number of molecular orbitals are equal to the number of atomic orbitals combining. Suppose if 4 atomic orbitals are combining, then it will lead to the formation of 4 molecular orbitals, out of which half new orbitals have energy higher than atomic orbitals, and half of the orbitals have energy lower than the atomic orbitals. The orbitals which have lower energy are termed as bonding orbitals, and those which have energy higher are termed as anti-bonding orbitals. Now, before understanding about this theory more, let us have a look on the concept of LCAO, that is linear combination of atomic orbitals. LCAO. As we all know that in wave mechanics, atomic orbitals are expressed by wave function psi. These are obtained as solutions of Schrödinger wave equation. Just like this, the Schrödinger wave equation can be applied to obtain the wave function of molecular orbitals also. And how is it possible? Let us understand. Suppose we have a diatomic molecule H2, and its atomic orbitals are represented by xi A, and for the second atom by xi B. Then, according to the concept of LCAO, that is linear combination of atomic orbitals, the molecular orbitals in hydrogen can be represented by xi molecular orbital is equal to xi A plus minus xi B. If we are talking about the bonding molecular orbital, then xi bonding is equal to xi A plus xi B, and xi anti-bonding is equal to xi A minus xi B. Now if we find out the probability density of molecular orbital, then it is given by xi bonding square, which is found to be equal to xi A plus xi B whole square. On solving it, we get xi A square plus xi B square plus 2 xi A xi B. From this, we come to know that the shared electron density is higher by the sum of xi A plus xi A square plus xi B square. And this value, which is higher, is found to be equal to 2 xi A xi B. This shows that the electrons in bonding molecular orbital experience greater force of attraction, and hence they have lowering in their energy as compared to individual atomic orbitals. Similarly, if we find the probability density for anti-bonding orbital, then xi anti-bonding molecular orbital square is equal to xi A square plus xi B square minus 2 psi A psi B. This shows that anti-bonding molecular orbital has lowering of electron density. Then atomic orbitals by the value of 2 psi A psi B. If we understand this concept with the help of diagram, then we can understand like this. Say it is 1s orbital of hydrogen combining with another orbital of another hydrogen, leading to addition overlap, and there occurs increase in the density. Some higher density would be found in this particular area. So it is xi A, this is for xi B, then this is xi A plus xi B, and such a orbital is sigma 1s orbital called bonding molecular orbital. For anti-bonding molecular orbital, there occurs subtraction among these two orbitals of hydrogen, xi A and xi B, leading to decrease in the electron density, forming sigma 1s star orbital. This is the node, and such orbitals are termed as anti-bonding molecular orbitals. It can be further understood with the help of an energy diagram, relative energy diagram. We take one orbital of hydrogen, atomic orbital of hydrogen, and the molecular orbitals which are 2 in number, formed due to the combination of two atomic orbitals of hydrogen, 1s and 1s. Then the molecular orbitals, which are 2 in number, one lies above the energy level of the atomic orbitals and second lies below the energy level of the atomic orbitals. The one that lies above is the anti-bonding orbital denoted by sigma 1s star, and the one that lies below is sigma 1s. This is the bonding molecular orbital. Molecular orbitals are of two types: sigma molecular orbital and pi molecular orbital. If we talk about the sigma molecular orbital, then we'll find that they are cylindrically symmetrical around the internuclear axis. They could be formed by the addition of orbitals or by the subtraction of orbitals. The 2px and 2py orbitals lie perpendicular to internuclear axis and they lead to the formation of pi molecular orbitals. The 2pz orbital lies along the internuclear axis and leads to the formation of sigma bond. Now let us see the energy level diagram. The major use of molecular orbital theory is to write the electronic configuration of the molecules as we write it for the atoms. The molecular orbitals are represented like this: sigma 1s, sigma 1s star. Star stands for anti-bonding. Sigma 2s, sigma 2s star. Sigma 2pz, since 2pz lies along the internuclear axis, that is why it will be forming sigma bond. Sigma 2pz star. Pi 2px, pi 2py, pi 2px star and pi 2py star. Now if we arrange these molecular orbitals in the increasing order of energies so as to fill the electrons in them, then the order up to 14 electrons is sigma 1s, sigma 1s star, sigma 2s, sigma 2s star. Pi 2px is found to be equivalent to pi 2py in energy. Then sigma 2pz, pi 2px star, pi 2py star, sigma 2pz star. This is the order up to 14 electrons. But above 14 electrons, there is a little bit of change in the order of molecular orbitals on the basis of their energy. Now the order above 14 electrons is sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, sigma 2pz now comes before. Pi 2px is equal to pi 2py, pi 2px star is equal to pi 2py star is less than sigma 2pz star. Electronic configuration of molecules we will see now. Before this, let us understand when is a molecule becomes stable. A molecule is stable if number of bonding electrons is more than number of anti-bonding electrons, and it becomes unstable if number of bonding electron is either less or equal to number of anti-bonding electrons. One more concept is there. that is of bond order. Bond order is equal to half the difference between number of electrons in bonding molecular orbital and anti-bonding molecular orbital. That is, bond order is equal to half N B minus N A. Bond order conveys various information that if bond order is positive, the molecule formed is stable. If it is negative or zero, molecule is unstable. This is the first point. Second is bond order is directly proportional to bond dissociation energy. Higher the bond order, higher is the bond dissociation energy. Bond order is inversely proportional to the bond length. Bond order also gives the information about the number of covalent bonds present in a molecule. If bond order is fractional, then it shows the paramagnetic nature of the molecule. Let us now see the energy level diagrams and the bond orders of some of the molecules. Starting from hydrogen. Hydrogen H2 molecule has 2 electrons in it. So if we write the configuration for H2, the configuration will be sigma 1s 2 and its bond order will be 2 minus 0 upon 2 is equal to 1. This bond order can be better understood with the help of the energy level diagram we can make for hydrogen. We make the energy level diagram for hydrogen where one atomic orbital of hydrogen is represented and then the molecular orbitals of hydrogen molecule are represented as follows. This is the atomic orbital of second hydrogen atom. 1s orbital of one hydrogen, 1s orbital of second hydrogen. Both are having single electrons in them. And in the molecule, we have 2 electrons and both the electrons are occupied in the bonding molecular orbital, that is sigma 1s. Sigma 1s star anti-bonding molecular orbital is vacant in this molecule. And so we get the number of bonding bonding electrons is equal to 2 and number of anti-bonding electrons is equal to 0. And so the bond order comes out to be 1. This bond order also shows that this molecule has single covalent bond and it is diamagnetic in nature. Second, we'll see the example for hydrogen molecule cation, that is H2 plus. The number of electrons in H2 plus is equal to 1. Again, if we draw the diagram for it, diagram would be the same as that of before, but number of electrons in the bonding and anti-bonding molecular orbitals will vary this time. How they vary, we will understand with the help of this diagram. 1s orbital of one hydrogen, 1s orbital of second hydrogen. Number of electrons is 1 here and no electron. Since it is an ion, so no electron is present in say second atom. Then the orbitals formed are sigma 1s and sigma 1s star. Since we have only one electron, it would be occupied in the bonding molecular orbital. Now the number of electrons in bonding molecular orbital is 1 and that in anti-bonding is 0. Bond order comes out to be 1 upon 2, 1 minus 0. that is 1 upon 2. This shows that the cation has paramagnetic nature. Now we see the configuration of helium molecule by the use of this theory, that is He2 molecule. He2 contains 4 electrons in it and its configuration will be sigma 1s 2 sigma 1s star 2. Bond order will be equal to half 2 minus 2, that is 0. This shows that this molecule do not exist at all since bond order is 0.